When introducing the fundamental theorem of calculus, the importance of the following formula is often downplayed, or it is hidden in an obscure discussion of limits. To be more specific, this version of the equation is often downplayed. To see why this formula is so important, consider the two graphs below. The graph on the left is of the function f of x equals 1/16 of x minus 3 cubed plus 3. The graph on the right is the derivative of this function. Now consider several points along the graph of f of x. The space between each consecutive point is 1 unit. In other words, delta x equals 1. The line segments connecting these points can be used to approximate the graph of f of x between x equals 0 and x equals 8. This piecewise version of f of x makes it easier to find the average rate of change between 2 points on f of x. This is where the fundamental theorem of calculus begins to take shape. The average slope of f of x between x equals 0 and x equals 1 is 1.1875. On the coordinate plane to the right, we can represent this slope as a rectangle with a height of 1.1875. Because the average slope of f of x is 1.1875 across the entire interval of delta x, we can say that the rectangle on the right has a uniform height across delta x. Thus, the area of this rectangle is m1 times delta x. Since delta x equals 1 and m1 equals 1.1875, the area of this rectangle is 1.1875 square units. You may also recall that the change of f of x across delta x is delta y equals m times delta x. We can display this change in y as a vertical line segment on the coordinate plane of f of x. The height of the line segment on the left equals the area of the rectangle on the right. We will now calculate the slope between x equals 1 and x equals 2 and represent this slope as a rectangle on the right and the change in f of x as a line segment on the left. The slope between x equals 2 and x equals 3 and so on through x equals 8. If we sum up all of the delta y's on the left, we get a line segment with a length of f of 8 minus f of 0. Which is equal to the Riemann sum of all the areas on the right. When we fill in the specific values for each term, both sides of the equation produce the following result. The net change of f of x between x equals 0 and x equals 8 is 9.5. And the Riemann sum of all the areas under f prime of x also totals to 9.5. Now suppose we wanted to get a better approximation of f of x. In this scenario, delta x equals 0.5. The average slope between x equals 0 and x equals 0.5 is 1.4219. When we represent this slope as a rectangle on the right, the height of the rectangle is the slope, or 1.4219, but the area is 0.7109, which is also the change of f of x between x equals 0 and x equals 0.5. We will do one more iteration of this process between x equals 0.5 and x equals 1. The height of the rectangle on the right is 0.9532. But the area is 0.4766. Which is also the change of f of x between x equals 0.5 and x equals 1. And if we continue this process through x equals 8, we find that the sum of the line segments on the left still equals the sum of the areas on the right. When we fill in the specific values for each term, once again, both sides of the equation produce the following result. The sum of all the line segments on the left totals to 9.5. And the sum of all the areas on the right is also 9.5. Thus, the approximate area under f prime of x is 9.5 square units. Even though there are more line segments on the left and more rectangles on the right, the length of each line segment and the area of each rectangle is smaller, so the net sum of the lengths and the net sum of the areas remain the same. This is true no matter how small we make delta x. For example, here delta x equals 0.25. Delta x equals 0.20. Delta x equals 0.1. And finally, delta x equals 0.01. In fact, as delta x goes to 0, the average slope of f of x becomes the derivative of f of x. In other words, the average slope becomes f prime of x. So the slope equation that we started with changes as shown below. And thus, in general, over the interval of x, a, b, the sum of each infinitesimal dy equals the sum of each infinitesimal area f prime dx. Or in calculus terms, f of b minus f of a is equal to the integral from a to b of f prime of x times dx, which in this specific example is the integral from a to b of 3/16 x minus 3 squared times dx. Even though we may not know the exact area of every rectangle in this infinite sum of rectangles, we do know that the area of each individual rectangle on the right is represented by a tiny change in f of x on the left. This tiny change of f of x is squashed somewhere into the line segment on the left, that represents the sum of all dy's throughout the interval on f of x. This is the most crucial concept in the fundamental theorem of calculus. We do not have to sum up an infinite series of rectangles to know the area under f prime of x. We can merely replace that infinite sum of rectangles with an infinite sum of dy's, which we know has a length of f of b minus f of a.